Right, we're going to look at one more example of a problem with inclined planes, but this time we're going to throw friction in the mix and we're going to show you how we deal with this. So we're going to have a truck. It's going to drive up a steep hill in San Francisco that's at an incline of 50 degrees. So those of you that have been to San Francisco, you know that that's not an exaggeration. That is a place where if you're going to walk, you better have strong legs. So we're at an incline of 50 degrees to the horizontal. So the engine of this 1,500 kilogram car, it's able to supply a force of about 30 kilonewtons, while the force of friction acting between the tires and the road supplies a force of friction of 14 kilonewtons. So we want to find the magnitude of the car's acceleration up the hill. Alright, this one is going to be a little bit more challenging, but we can still do it. So for this, I don't know why I do this. Sometimes I'd still like to draw out the actual incline. It's just who I am. So here's my incline. There's my 50-degree angle. Here's my truck. Don't mind it. It's pretty ugly looking, but it's going to do the job. So there's my truck. So what we're going to have for a free body diagram, kind of referencing that. So my FBD. So my free body diagram, this one's going to be a little bit more intricate this time. So I'm going to have that force of gravity that's going to go down. I'm actually going to write FG there because I'm going to not want that there. My normal force is still going to act normal to that surface. So we're going to have something that looks a bit like this. It should come from the dot there. I didn't align that very well. So I'm going to cheat and maybe make the dot a little bigger. There we go. Now we have to look at the other bits of information that have been supplied. So we've been told that this car is going to supply a force of 30 kilonewtons. Think of this like an applied force. So this applied force is going to be directed parallel with the plane, but it's going to be going up this hill. So we're going to want that FA parallel with this surface, and we're going to want it directed up this way. And then we're told that there's a force of friction between the road and the tires of 14 kilonewtons. We're going to want that directed against the direction of motion. So if this object's moving up the plane, force of friction is going to have to work against us here. So we're going to have this force of friction going down the plane. Now the other thing we'll want to do with our force of gravity, we're going to break it up into components. So my force of gravity, we're going to break that up into an FG perpendicular, and we're also going to break that into an FG parallel. And that angle in here, this angle is going to be our 50 degrees. Sorry, it's not very clear there. Let me try that again. 50 degrees. So our free body diagram, it looks really complex. There's a lot going on in there. We're going to take it slow. We're going to take it steady. One thing to note, the moment you break up the force of gravity into components, you will not need this FG vector again. The whole purpose of decomposing it is so that we don't need it for future use. So we need to call some directions positive. Now again, perpendicular to this plane is going to be my Y direction. And since this thing is driving up the plane, we're going to call up the plane parallel to that surface. We're going to call that our X direction. This is what we're going to call positive. So we have a lot going on here. We're going to take this really slow, and we're going to go from there. So let's see what we got going on. So we're going to look at net force parallel to plane. So parallel to the plane, I have a few things going on. So parallel to this plane, first of all, I have this applied force that's going up. I have this force of friction that's acting against this motion. And the one that students always forget, don't forget, acting parallel to the plane, we also have this parallel component of the force of gravity. And students forget this one. So we have to be really careful. We want to make sure that that gets included. So my net force, we know that that's just going to be MA. And then we have this applied force plus this force of friction plus mg sine of theta. Now again, I'm going to have to explain the signs on this in a moment because this one's going to get real complex really fast. So I want to divide everything by mass here. So we're going to divide by mass. We're going to divide by mass. Now keep in mind, even though this has an m, we can't cancel this m out directly because there has to be a mass in every term. So we're going to have to leave this as is. So I'm going to have A parallel is FA plus FF plus mg sine of theta, and then divided by m. So this is where the sign convention is going to get a little bit tricky. FA and FF will be fine. We have to be really careful though with G here, and we'll explain that in a moment. Now, my applied force, it's up the plane. We've called up the plane positive. It's 30 kilonewtons. So we're going to have this 30.0 times 10 to the 3 newtons because we want this in newtons. We have this force of friction acting against us, so that has to go in as a negative since that's going down the plane, and we've called up the plane positive. So this is going to be minus 14 kilonewtons, or minus 14 times 10 to the 3 newtons. Now the last thing that we have to be careful with is we have to be careful with G here. So we still have the mass of this car. It's 1,500 kilograms. Now, because we have called sort of this up the plane positive, this whole upwards direction is what we're defining as positive. G is still going to act down in this case. So in this case, we're still going to define G as being negative. Because with G going down, it's going to have a component that is in the negative y direction and the negative x direction. So we're going to put this in as a negative 9.81. The other, I'll call it more simplified explanation for why that is this force of gravity parallel. It's opposing our motion, so we're going to have a negative in there somewhere. Because this force of gravity parallel, it's not trying to get the truck up the hill. It's doing everything to try and pull it back down, so it's not helping out here. And then we got sine of 50 degrees. And then we're going to divide this whole thing by the total mass. So my recommendation when you're putting this in the calculator, do the entire numerator first, get that number, then divide that by 1,500. You will experience a lot less frustration doing it that way. Otherwise, you may end up with some calculator errors. So we're going to punch that into the calculator. We're going to be really careful with that. And again, with these questions, take your time. There's no rush. So what I'm going to get here is I'm going to get about, we'll call it 3.1518 meters per second squared. Or I could say that the magnitude of the acceleration of this truck up the hill, it's about 3.15 meters per second squared. So the big thing you have to watch for, first of all, we want to make sure that we are converting the newtons or the kilonewtons to newtons. We want to watch our sign convention since FF is opposing the motion. It's going down the plane and we've called up the plane positive. We want that negative there. And again, because we've called essentially upwards, like up the plane and upwards perpendicular plane positive, G has to go in as a negative here, so we got to be mindful of its sign. And that one's going to be the tricky one with inclined planes. My recommendation, see what FG parallel is doing. If it's helping you out, like if it's going in the same direction as the net force, it's going to add to it. If it's going against the net force, it's going to subtract from it. That would be my recommendation to how to approach that one. So we did a lot of work. Now, part B, so the truck, it's going to start at rest from the base of the hill. So we want to determine how long, or the time, it's going to take for this to reach a speed of 50 kilometers per hour. So we know a few things. It starts from rest, so we know VI is 0. We are interested in the time. We know the acceleration, my unrounded value of 3.1518 meters per second squared. And then we have this final speed of 50 kilometers per hour. But we are a metric country. We do not like kilometers per hour. So 50 kilometers per hour. We're going to divide that by 3.6, and this is going to give us about 13.8 repeating, or we'll say 889 meters per second. So I need an equation that has A, VI, VF, and T. So the equation that's going to come to the rescue here is A equals delta V over delta T, or in its more useful form, A equals VF minus VI over T. So this is nice actually. VI is going to be 0, so this is going to simplify very beautifully. So VF minus 0 is just going to give us VF, and then we have VF over T here. So the objective is to solve for the time. Again, if what you're solving for is in the denominator, you need to bring that up top first. So we're going to multiply both sides by T, and what we're going to get here is we're going to get this AT equals VF. Now that I got the T up top, I can isolate, divide both sides by A. So I'm going to get that the time is equal to this final speed divided by the acceleration that we'd previously calculated. So my final speed is that 13.889 meters per second. Make sure that is in meters per second and not kilometers per hour. And then we're going to divide that by that acceleration, about 3.1518 meters per second squared. So both of these are unrounded values. So the last thing we want to do is we want to just punch that into the calculator. And we're going to get about 4.41 seconds. So for this truck, it starts at rest at the base of this hill. It's going to accelerate at about 3.15 meters per second squared. So based on that acceleration starting at rest on the bottom of the hill, it'll reach 50 kilometers per hour in about 4.41 seconds. So this is a much more challenging problem with inclined planes because there is a lot to consider. As with everything in forces, be really careful with directions, make a carefully labeled free body diagram, and that will help you significantly, and it'll certainly cut down on the frustration.